Hello everyone. So today we will be continuing the chapter which we were studying. So the topic is dispersion, dispersion of white light by prism. Right. So first of all, we need to understand what is a prism. So prism is actually a triangle shaped object like in 3D space. Suppose it is shaped like this, right? So it is somewhat shaped like this. So these are the three surfaces, right? So this prism has these surfaces. One surface is this side, and the other surface on the back side, the green colored one, right? So also a base, right? So this is a prism. So what is the case we are taking is dispersion of white light by a prism. So dispersion means splitting of light or white light into its constituent colors. Right. So what happens? This white light is made up of seven different colors, which are we write it in this order. Please remember this order because this is how the order of dispersion will be when we pass a beam of light through this prism. Right. So this is your order of white light. Like when you pass, so this is your prism. Now let me draw the ray diagram. So I will draw the front view. Okay, then from the front, this will be appearing like this. Suppose this is your prism and a ray of light, white ray of light. Let us say this is a white beam of light. This is coming like this. So what will happen? You know that this is the normal. This is the surface. We are having triangular and on a prism. These three angles are 60-degree. Right. These angles are 60-degree. Means that triangle shape is what? It is an equilateral triangle in a prism. So this is the incident ray of light, which is a white beam of light. And we know this is a first surface, like it is inclined to 60-degree. So what will be the normal to this surface? This will be the normal, right? This is the normal to this surface. And if I consider normal to this surface, it will be somewhat like this, right? So what happens? So what happens? This beam of white light, what will happen? It will get refracted towards the normal because what will happen? This is a rarer medium here. Here is a denser medium, right? So first of all, we will be seeing the refraction. So what will happen? This white ray of light will be bending like this. Okay. Suppose I am placing two all pins here, right? This is all pin one, right? This is first pin, this is second pin. And if you are trying to observe from here, right, what will happen? This ray of light is getting refracted towards the normal, right? And if I consider this normal at the this point of incidence, so what is the normal here? It is like this, right? This is normal. Now what will happen? It will be bending away from the normal. This is the normal because this is denser medium. Again, there is air. So what will happen? It will bend away from the normal and emerge like. So what has happened? This is the path of ray. So you will be observing the all pins as here only, right? You will observe the all-paleness on the air, because you will see that if you observe from this side also, suppose you are observing from this side also, what will happen? This all plane will appear here. So this is how refraction is taking place in a prism. This is about refraction, right? Now we are seeing refraction. So I have explained you this dispersion. So this is what? This is actually, first of all, we are seeing refraction. This we will be seeing just in a while. First we see what is refraction. So this is refraction, right? And we have some terminologies, right? Suppose this incident ray is traced backwards like this, right? Traced backwards like this. Let me change the color so that you can see. So suppose this was traced backwards, right? And this is your, because it is emerging from this surface and it is final ray, okay, final refracted ray. This is called as the emergent ray. This is called as the emergent ray. This one is called as the incident ray, right? And this angle, particular angle, is called as the E angle. That is, angle E is what? Angle of emergence, right? It is the angle of emergence. And from the original incident ray, if you consider this deviation, right? Suppose this was the original incident ray and this was your original emergent ray, right? This is your, this, if I extend this backward like this, then the angle made between this point, right, between this extended incident ray from backwards and this emergent ray, this angle is called as angle D. This is angle of deviation. This is angle of deviation. This is emergent ray. This is angle of emergence. This is angle of deviation. So let me tell you what is angle of deviation. Let us suppose to draw it here. This was your incident ray, right? It got then refracted, then emergent ray like this. So here was the normal, right? Here was the normal, right? Like this. So if I backtrace this incident ray and if I backtrace this refracted ray, then this angle was angle of deviation. And from this normal, this angle is made by this ray is angle E, that is angle of emergence. That is how I was talking. So this is your refraction. Now what happens if we observe it minutely, right? If we observe it minutely, what happens? If I consider a prism like this, let me draw much bigger, right? So if this is your prism, like this is the front view, and now the white lies it is an incident, right? Let us say white beam of light, because it should be a beam of light for proper dispersion. Then what will happen, since we know this is a air medium, this is your glass, which is a denser medium. Now what will happen, you know that white light is made up of 7 colors, right? White light is made up of 7 colors, which I told you. So these 7 colors are violet, indigo, blue, green, yellow, right, orange, and red. So what will happen? These, all these are arranged in top to bottom, that is decreasing order of wavelength, right? This is your decreasing order of wavelength. So wavelength is represented by lambda. This is called as the wavelength of colors, right? So white light is made up of 7 colors and each color is having some different wavelength. So in which red is the having the largest wavelength and violet is having the least wavelength. So what will happen? The colors which are having the least wavelength, right? What will happen, due to this denser medium, all of these colors, all of these, or we can say white light, will suffer refraction. But what will happen at this point, as it enters the denser medium, this white light is consisting of 7 different colors and each color is having different wavelength. So depending on the value or wavelength, the larger wavelength, the color having the larger wavelength will have the highest speed, right? So this red color and violet color, right? So this has highest wavelength, right? And this has least wavelength. But the speed, if we talk, the speed is highest in this red because this is the largest wavelength light, and so speed will be more, and the speed is further reduced when it enters a denser medium. So what will happen due to the different speed, because here now an angle is involved. So after this angle, when they bend, what will happen? As they bend, due to this different angle of we can say refraction, because these will have all will have different speed, and they will suffer from different angles, right? So what will happen? They will start to form into different colors, right? So they will be starting to form into different you can say constituents. And what will happen when they reach this surface? Again, these rays of light will be emerging with a different angle. All these rays of light colors, like what will be the colors? Now what will happen? All these colors will be separated. When you see from this side, you will see a band of light. You will see a spectrum of light, which at which bottom will be violet and at top will be red, because what will happen, this is the ray of light which will be least bending, right? It is the least bending, and the least bending will be happening in the light, the color having the highest wavelength. So red is having the highest wavelength, and that is why it is traveling at a much larger speed. And as it is traveling faster, suppose it is cost the denser medium will force it to bend, right? Suppose the thing is traveling fast, so it will be bend least. You can consider this as a river. Suppose water is flowing like this, okay, water is flowing like this, and continuously what this water does, if a boat is traveling, okay, if a boat is crossing this river like this in this direction, if the boat is crossing from this end to this end, what will happen? This flow of river will push this boat here, and if this boat is having a higher speed, it will there will be a less distance which this boat will be taken by the flow of water, right? So this flow of water effect will displace the boat in this direction very less if the speed of boat is more. So that is why you can consider a similar case here, that red light is having the highest speed. So as it is having the highest speed, it will bend the least, okay, and it is having a larger wavelength. So it will bend the least, and that is why it will be at the top. When you consider this angle of emergence, at every point you can draw the normal and see the angle of emergence. Just now I told you that after refraction from this prism, this ray of light occurs, and this from normal, if you say, this is the angle of emergence. So if you see angle of emergence, what will happen? The red will be having a angle of emergence, which is which will be what? When you compare it with the incident ray of light, it will be least, okay, and violet will be having the most angle, the largest angle of emergence. So violet appears at the bottom. So this is the order with your, okay, so this is the order which you must remember from top to bottom. This is the decreasing wavelength, okay, the wavelength decreases when you go from top to bottom, and this is the color spectrum which will be you will be observing. This is the correct color, correct order of the spectrum. This is called as dispersion of white light. This is called as dispersion. Dispersion means that each part of everything, suppose a thing is made up of 7 or 8 different parts, and it gets split into those parts. So that is what is called as the dispersion. So this surface of prism, these angles of prism, this equilateral nature of this prism forces this light to separate into several colors. That is how the dispersion of light occurs in a prism, right? So this is what prism case is. Now let us see some other cases also. Let us talk about rainbow. Right, rainbow. Now, before moving to rainbow, there is one more thing. So Newton observed a phenomena, like suppose he placed this prism like this, right? He placed a prism like this, Okay, and he placed a prism like this. Okay, two prism. So what he did, he made an incident ray of light on this. So what will happen? As you know, this will be spreading into the 7 colors. So what happened? These colors will pass through this prism, and then again the reverse of this happens, and you will observe a white light again. Here also a white light, here also a white light. So this observation, because when you place a single prism, it is splitting it into 7 colors, and he observed he placed another this prism in inverted position, then he observed again a white light. So this made him clear about that white light is made up of 7 colors, right? So this is actually nothing but a glass slab. If you join these two, it is nothing but this. Okay, a glass slab. So you know that in a glass slab, the opposite surfaces are parallel to each other. So when they are parallel, so whatever refraction is done by these, it will be reversed in this case. Okay, so this angle which was here, angle of incidence which was here, the angle of emergence will be same for all of the colors. So that is why it will appear to you as white light only. Okay, there is no deviation, there is no deviation involved from the incident ray. Whatever refraction is done here, it will be restored back when it enters this second plane, because these two planes are parallel. So same case happens here. This one and this one is parallel, and this one and this one is parallel. So two prism act as a singular glass slab. So there will be, finally you will observe white light only. Okay, now there is a concept involved in rainbow. Okay, so rainbow is what? It is related to this dispersion of light only. Suppose it is a for this two condition must be favorable. First must be it will be a rainy day, rainy or rain droplets, such that observer observer observer's back is towards the sun. Okay, observer's back is towards the sun, and sunlight is should be there, right? Well, when two conditions are there, because rain is also happening and sunlight is also coming, then what will happen? Suppose this is your sun, right? And you are standing like this, right? So what will happen? And this is the place where rain is going on, right? Very light drizzle is going on. The rains are going on here. It is cloudy over here little bit, and the rains are going on here. So what will happen? These light rays will be incidenting on this uh, tiny droplets, and these tiny droplets act as very little prism. So what will happen after reflection and dispersion from this prism? This will reach your eyes, right? So these 7 colors you will be seeing. Okay, so that is what happens in a class in a case of rainbow. So rainbow, what happens? You are able to see, observe that in a rainbow, the top color is what? This is red, and this is going to be violet, because I told you that violet is having the least wavelength and the least speed. So it will be refracted more, and that is why it will appear in the bottom of the spectrum. So this 7 colors, when are appearing as a band, this is what we call as spectrum, right? So it will be occurring on the bottom part of the spectrum on the so why? So these two conditions are necessary, that the sunlight must be on the backside of the observer, and the sunlight then after striking these tiny droplets behaves as a prism, and then these 7 colors will be observed by this observer. So that is why rainbow is formed. And now let us see one or two cases which involve this concept of atmospheric refraction. Okay, what is atmospheric refraction? So atmospheric refraction is what? First you need to consider that hot air is rarer. Okay, because you know when you increase the temperature and when the air is heats up. Okay, in ninth class we have already studied that when the temperature is increased in a gas, because air is a gas. So now in a gaseous state, when temperature is increased, the molecules will be far apart from each other. Okay, so when they are apart from each other, what will happen? This air will become optically rarer also. So we must know that cold air is always a denser one, right? So when the air becomes heated up, it goes up, it becomes rarer. Okay, so there is a slight, and this temperature is continuously changing. It doesn't remain constant. So what happens? This refractive index of hot air, always you can see that refractive index of this will be, because this is a rarer medium, so refractive index will be less, right? Refractive index will be less, and in this case refractive index will be more. So due to this difference in refractive index, there will be refraction. So that is why sometimes you might have observed, suppose an outside, when a person is cooking some of the food, right? Some of the food is cooking in oil, like that. Okay, so what happens? The hot air will rise up. The hot air will be here, and the temperature of the air is not even, and it is also continuously changing. So when you are trying to observe, what happens? The wavering occurs. You can see wavering. Okay, wavering occurs like something is vibrating when you see in just top of the container. Okay, where a person is cooking a food outside. Okay, you can see a wavering kind of thing, is like something is fluctuating, that kind of thing happens, that is wavering. So what happens? Because there is continuous temperature change, there is a hot air, and hot air is rising up. So hot air rises up, and from here the temperature will be high, then here will be high, then here will be high, then here will be high. This air is going up. So there is continuous temperature change, and there is continuous refractive index change. So to your eye, what happens? The ray of light is continuously bending. Okay, bending, and it is at different time. It is at different place. So it also, the eyes reaching your eye also like fluctuating. So that is why you are observing that something is like wavering. So that is the case of a atmospheric refraction. Also, in case of a twinkling stars, you have seen, this is because this is a more frequently asked question, mentioned in our textbook also, twinkling of stars. So why it happens? Because suppose this is a star, so stars distance, the distance of stars are very far away, right, from us. So distance is very large, so that is why, and these stars are not small, stars are actually very huge, but they are very wide, far away from us, so they appear as, you can consider as point sized, right? These are point size. So this is a star, suppose this is a point, then you will be, observer will be very, very, so many kilometers and kilometers and kilometers and kilometers away from this star. And what happens? I told you that the temperature of air is not even. Okay, when the hot air rises up, suppose it is a denser, rarer at on the top. So what happens? This ray of light, it must go like this, right? If there is a one medium only, if the refractive index is only, let us say, air, or let us see a uniform, some constant, let us, this constant we consider it as, let us say, n. If it remains uniform, then this straight light will be reaching your eye, and you won't be seeing any twinkling. Twinkling means what? At one time instant, the star becomes bigger and smaller, or like that you see. Okay, or its position keeps on changing. That is why apparent position is keeps on changing. That's why you see this twinkling effect. Now let us see how it has happened. So suppose there is only one material, then it will be a constant, then there will be no twinkling. But now what happens? As I told you, there is atmospheric refraction. Now due to this atmospheric, because there is presence of atmosphere on earth, so due to this small atmospheric refraction, in space there is no air, let us say. At the point of star, there is no air, and when it enters the atmosphere, due to atmosphere, let us say, it bends to somewhat. Okay, what happens? This ray of light is coming like this. Okay, now what will happen? This is your, let us say, observer. Okay, there is an observer. Now this ray of light, what happens? It comes like this, and due to atmosphere, it will be bending. Okay, it's somewhere, let us consider, because so many times it will get refracted in the atmosphere, and the cumulative effect, the final effect, we see like this. Suppose it gets refracted like this. Okay, and then to our eye, because of this refraction, to our eye, we see that, suppose these rays are coming from this point. Okay, then to our eye, it says that this position of a star is this. Again, as I told you, that the temperature is not a constant thing in atmosphere, it is continuously changing, and that is why this refractive index of air will be changing continuously. So what happens? According to the refractive index at a particular instant of time. At every instant of time, the refractive index value will be different. So the refractive index is changing. So as this refracted ray, sometimes like it will be bent like this, sometimes it will be like this, sometimes it will be like this. So different position of stars will be at different point of time. So what will happen continuously? This is going from this to this. Continuously, this position keeps on changing. So this is called as this is a real position. Let us say this is a real position. Then these all are apparent position, right? So this is apparent position, and what happens due to this? This there is a continuous position change, virtual position change. It appears to our eye this position of stars is changing. It appears to our eye because of this atmospheric reflection. It appears to our eye that the position of star is continuously changing, and we observe that the star is, let us say, it appears that it is a twinkling. So that is how it occurs. Now there is another case in which we call that why. There is a question why planets don't twinkle. So there are two reasons. I told you that stars are very far away. Stars are very far away. But in case of this planets are not that far as compared to these stars. These are a bit nearer to us. So what will happen? Suppose I draw a dot here, right? This is a dot. I ask you to observe this from very close to eye. It will not appear to you as a dot. It will appear to as a filled circle with yellow color. Okay. Now let us say observe this from 10-meter distance. Okay. Increase the distance of your eye from this circle. What will happen? After some distance, it will appear to as a point only. So that is what it happens. In case of planet, the distance is not very large as compared to stars. So they are nearer to the observer first of all. So they don't appear as point size. So they will not appear as point. Since they are nearer, they won't appear as point size. They will be something like larger to the observer. They will be larger. So what happens? This refraction effect, although there will be a apparent position change. Okay. Sometimes refraction will be like this. Sometimes it will be like this. Okay. Sometimes it will be like this only. Different position will be there. But what will happen? It will be in the vicinity of this size. So what will happen? Since this is larger, and this has so many points can be considered, okay, for this real position. Okay, so that is why, although if there is a shift, the shift range will be like this only. The apparent shift range will be like this only due to this atmospheric refraction. The apparent shift that we observe will be in this range, and it will not be uh, out of this zone where it crosses the size of the planet. So what will happen? It will appear to as stationary only. Although there is atmospheric refraction going on, but the all of the atmospheric refraction effect will be nullified by due to this large size of planet. And why large? Because it is much nearer as compared to stars. So position of a point, you can see it is changing. Okay, it is the same thing. If I suppose if at 10 meters you are able to see this filled circle like this. Okay, at 10 meters you are able to see filled circle like this. Okay, at 20 meter you are able to see like this. Okay, but what I do, I want that at 20, suppose if I increase the size of this, and at 30 meter you are observing like this. Now if I what I do, at 30 meter, let us say you are observing it as a point size. So this was at 10 meter, this was at 20 meter, 20 meter from the eye. This is let us say these are all imaginary numbers, okay, for understanding. And at 30 meters you are seeing point size. Okay, suppose if this size would have been larger, then in that case you would have not been seeing it as point size. So that is the case with planet, because planet size is larger, and that is why they won't be appearing as point size. So this amount of atmospheric refraction will produce the apparent shift, but that apparent shift won't be able to segregate this virtual location from the original location. It will be fluctuating in this range only, which is the original size. So you won't see any twinkling in case of planets. This is how the case is observed in case of let us say planets. So this was about atmospheric refraction. Now one more case is also there, which is regarding the early sunrise and early sunset of sun, right? We are seeing the sun rays reaching to our eyes 2 minutes early. So why this happens? Let us understand this. Suppose this is your, let us say this is your Earth. Okay, Earth is, you know that it is not flat. It is somewhat spherical, not perfectly spherical also, but somewhat spherical. So what happens? Suppose this is your observer standing here. Now the what we call as the sunrise. So this is the line of the, let us say, surface. Okay. So when the sun crosses this line, then we call it as sunrise. Okay. Suppose here is the sun. Okay. Here sun is there. Now actually in real time we are saying real position of sun is here. But what happens, as we know, these rays of light, it is emitting light. Okay, so this rays is coming, but due to this atmospheric refraction, it will be, let us say, bending. Not this much bending, but for understanding, let us consider slight the bending is there. Now bending is there. What will happen if you observe these rays? Due to this bending, this appears that these rays of light are coming from this point. So you will observe that the sun is here. So this is what virtual position of sun. And this was what the real position of sun. But to the observer, it appears that this sun has already crossed this surface or has already passed the horizon. It is above the horizon, and you will see a early sunrise, which is around 2 minutes. Early sunrise. Why? Due to atmospheric refraction, it is happening. And same case occur in case of a sunset. What happens in sunset? Again, let us see. This is the observer. Now in this, this is the surface point. We will call sunset as when this crosses the sun goes below the horizon line, then it will be a proper sunset. Now what happens? Although when this sun, let us say it is here, the sun has already set. Okay, the sun has already set. It has already gone below the horizon line. But again, due to atmospheric refraction, suppose these are the rays of light traveling, and again due to refraction, they will be bending. Okay, they will, these rays of light will be bending, and it will appear to the observer that this sun is still above the horizon. So this is now what? Delayed sunset. So that means what? There is early sunrise and delayed sunset due to this atmospheric refraction. So three things we have observed. First is the twinkling of stars. Two things actually, twinkling of stars and this early sunrise and delayed sunset is what we observe due to this atmospheric refraction. Now let us move to scattering. So this chapter is a bit more theoretical. Scattering means when a light strikes a certain object, it will spread in all directions. So that is what we call as scattering. Okay, that is what we call as scattering. Now in scattering case, we have a special case. Suppose we know that when there is a true solution, okay, you have studied that when a true solution, if a beam of light is passed in a true solution, it won't be observed in case of a true solution. But when you are passing it to a colloidal solution or suspension, what will happen? The ray of light or the light will be visible in the colloidal solution. So this happens due to what? Because you know that this uh, true solution particles. So the particles are what? Particles are smaller, right? Particles are smaller, and here this is the rough thing. Okay, exact size you can also tally, but the particles are comparatively larger. So what happens when there is a requirement for scattering? Suppose this is an object, okay, and if the light coming has a wavelength which is comparable to the size of the object, okay, size of the object, then in that case scattering will be occurring. Scattering will be occurring. So if the Rays of light strike these particles. Because these particle size is smaller, there will be no scattering observed. So what will happen? As there is no scattering observed, so what will happen? The light will not be visible. The path of light, the path of light won't be visible in case of true solution because the size of object is very small. In this case, the size of object is large enough. It is comparable with respect to the uh, wavelength of light. So what happens if it strikes the surface, if it strikes the material, right? If it strikes a material, what it will happen? It will be comparative. It will be comparable to the size of the uh, particle and the size of the wavelength. So what will happen when these two strike? There will be spattering or scattering of light everywhere, and then in that case we will be able to see this path of light. Why we are able to see the path of light? Because these are having a comparable wavelength. So that is how required case for scattering is. So that is why the scattering occurs. Now let me tell you one thing. There is also a case of Tyndall effect. So what is Tyndall effect? We have already seen this in the earlier class. So when from a dense forest, this ray of light is passing, right? This ray of light is passing, and then this path of light, this path of light, this path of light becomes visible, becomes visible. Suppose a sunlight is passing through a dense forest, right? Through a dense forest, what will happen? Due to the presence of smoke particles and other particles, what will happen? There will be scattering. There will be scattering, and due to this scattering everywhere, scattering in this path of light will become visible due to this scattering, and these smoke particles and air particles are comparable to the size of the wavelength of light, and that is why scattering will be happening, and this scattering, this minute scattering will be making this path of light visible. From a small beam of light is coming, then that beam of light will be visible due to this scattering effect, and this is called as Tyndall effect. This generally in misty condition or smoggy or foggy condition, we observe this Tyndall effect in case of a forest. Okay, this is also observable when in a closed room you open a window, right? Then these dust particles and the smoke particles or the dust particles make these beam of light visible due to this scattering that is called as Tyndall. Now there is another question sometimes asked, why the sky appears blue. So this answer is also due to scattering of light. And why scattering of light? Because we know sunlight is what? In sunlight is what? It is also constituting of 7 colors, which is, I told you what? And in this spectrum, the intensity up to green and this blue is more. Right, these colors are not that intense, okay, less intense in case of sunlight. So this is the major part of the band of, although these are also present, but very small amount of these violet and indigo are present in case of a sunlight. The intensity is very much less. So what happens when we have an atmosphere, right? An atmosphere present is air, and air is constituting of several components, several gases, in which nitrogen is the major one because it is around 70 to 71%. Then oxygen also, right? So these are nitrogen, oxygen majorly. So if and CO2 also. So these nitrogen is one, and there are smoke particles also, right? Smoke particles and dust particle present in the atmosphere. So this sunlight will be striking these particles, which are wavelength of this sunlight is somewhat comparable or larger or comparable to this uh, size of this particle, right? Now what happens? It will get scattered. Will get scattered. This light will get scattered. Now you know that what will happen? The least wavelength of the light will be more scattered. Okay, because why? The least wavelength and the more wavelength, because I told you that these colors are present in the majorly present. These are also present, but these are the more are these colors present up to blue. Indigo and violet intensity is somewhat less in sunlight. So this is also present. And this is what happens, as you know, the wavelength of red is greater than this wavelength of orange and then this wavelength of yellow. So this is the case which we are telling, that wavelength of red is greater than wavelength of orange, is greater than the wavelength of yellow, is greater than the wavelength of green, is greater than the wavelength of blue. So as there will be, due to this largest wavelength, there will be least scattering. Okay, and blue is having the most scattering. Why? Because as the wavelength decreases, it becomes somewhat more comparable to this size of this particle. But the wavelength of red is more. So wavelength of red is what? More than the size of particle. So here the refraction will be much lesser, scattering will be much lesser when compared to the blue color. So that is why blue lights get scattered the most, and that is why if it is scattered the most, if it is everywhere in the atmosphere, then it will be reaching to our eyes the most, and that is why we will majorly see the sky color as the blue only. Technically, that is why I told you earlier that wavelength of violet is the least. Wavelength of violet is the least. So we must see the sky as violet only. But that is not the case, because violet intensity is somewhat very less in this sunlight. Up to this green and blue, we are the major part of this. So this scattering is also there. Violet and indigo are also scattering, but that scattering is not sufficient enough, because an original sunlight, the constituent of this indigo and violet is lesser. So majorly this blue is there. So it what overpowers the scattering of other colors which are in the lower order, that is indigo and violet, and that is why we are able to see the sky as okay. And also there is a case of red colored sky, red colored sky in case of when sunrise and sunset time. So at sunrise and sunset time, you can observe that the sun is also sometimes appears red and the sky is also appearing red. So why it is that the case? The case is that because at this distance, suppose sun is here. So the most of the light which is reaching the earth, okay, in presence of atmosphere, all the colors scatter away. All rest colors scatter away. Colors scatter away. Okay, because at this point this sun is that very far away. Okay, there when the sun is here, there is a different case. It is sun is overhead or it is a daytime, it is the other case. At the time of sunrise and sunset, the position of the sun will be this at sunrise, let us say, in the east direction, and at sunset it will be let us say it will be at this place. So what will happen due to these larger distances, all the other colors will be scattered away, because we told that red has least scattering. Red is has color is having least scattering, because the wavelength of red light is very high, so scattering is least. So what will be happening? This red colored will be the only one, this red or orange, that is why orange and red tint we see. So that will be the major color which will be reaching your eye, and you are able to see only this red color of sun, and the sky in the vicinity of this, or the sky around this, also appear as red only, because all the other colors get scattered, right? So you need to remember that the wavelength, let me summarize everything for you so that you can answer any of the question related to this concept. So this is your with your okay, and if I mark like this, so this is your decreasing order of wavelength, right? So decreasing order of wavelength, that is mean, or I will write here also, wavelength of red is greater than wavelength of orange, is greater than wavelength of yellow, is greater than wavelength of green, is greater than wavelength of blue, is greater than wavelength of indigo, is greater than wavelength of white. Okay, and as this is having the most wavelength, this is having the least wavelength, what will happen? This is the or you can see if I draw this upside down, this is the increasing order of speed. Okay, so the speed of violet is the most, right? And what is the scattering? And this is also, if I draw this, this is increased scattering, right? So red is having the least scattering and violet will have the most scattering effect. Okay, because the wavelength of violet is the least. So that is how you will be answering these questions. Okay, it is based on scattering, right? So this was about the case of the, let us see now some of the numericals related to what we have studied earlier, right? First question is, an eye has a near point distance of 0.75 centimeter. What sort of lens and spectacles would be needed to reduce the near point distance to the normal value? Okay, he is saying that the near point distance is 0.75 centimeter. We know for a normal eye, you know that the near point, you must remember this, okay? Near point distance for a normal eye is minus 25 centimeter, okay? Or 25 centimeter if we're talking about the magnitude only. 25 centimeter, and the far point is infinity. But he is saying the near point is 0.75 centimeters. So you can see the near point has been disturbed. So what is near point? That up to this distance, the eye, closer to this distance, the eye won't be able to see anything. Okay, that means that near point is disturbed. Far point is fine. Far point is fine. For this eye, you can see that far point is fine, it is infinity only. So when far point is fine, it means it is far sightedness. The person is suffering from far sightedness, or what we call it as hypermetropia. So this is very clear. So once you know if it is hypermetropia, then also you can tell the lens is convex only. Now let us calculate the values first. So what sort of lenses spectacles would be needed? So I already told you that near point is disturbed, and it means near there is problem with something with the near point. Far point is okay. That means far sightedness. That means it is able to see far points very clearly, but not the near object. So for the worst case, when the object is placed at the near point, then the eye will have the most blurred effect. So that is that we will take the most worst case for the calculation of the appropriate value of the power of lens, because he's asking calculate the power of lens required. Okay, type of defect we have already answered, right? Lens also we know that for hypermetropia we need convex lens, but let us see now. And what will be the image distance? Image must be formed at minus 0.75. Actually this is meter. Okay, this is meter. So if I take this in meters, right? This question is specified in meters. So let us, if I take this in meter, that will be minus 0.25 meter. And where the image must be formed. Now the image of this object placed at the near point for a normal eye should be formed at near point of this eye. So it will be minus 7.75 meter. All the calculations are meter only. So what we will be getting is direct power only. So F we need to calculate. So 1 by F is what? Power. So now 1 by F is 1 by V minus 1 by U. So if I calculate this, that means minus 1 by 0.75. And this is minus minus will become plus 1 by 0.25. So this is what? Also minus 100 by 75 plus 100 by 25. So this is equal to what? Minus 4 by 3 plus 4. So this is 8 by 3. So 8 by 3. 1 by F is, or power is 8 by 3. We have calculated in meters only. So this is 2.667. That will be your in diopters, right? Power. and you can see the sign is plus. That means it is a convex lens, and already we know for correcting for correcting this far-sightedness or hypermetropia, we need only one. So this is how we solve the question. Now let us see another question. So an eye is able to see objects up to 2 meter clearly only. So that means up to 2 meter. It means what? This is an eye, and up to 2 meter it is seeing clearly. Up to 2 meter it is seeing clearly, and beyond this point it is not clearly. It is not able to see clearly. So what is the definition of far point? That the largest point or the farthest point up to which eye can see. So we can only mark that this is nothing but the far point of eye is what? 2 meters. What type of lens would be increased? Needed to increase it to infinity. Okay, the normal range, we know that the normal far point is what? It is at infinity. And calculate power of lens. Okay, first of all, far point, there is a problem with this far point. Problem with this far point. Near point is fine. Okay, it means near point is fine, which is 25 centimeter. Near point is fine. Near point is fine when fine means that it is near sightedness. That means near sightedness, all we call it as myopia. That the person is able to see clearly nearby objects because near point is is fine. There's a problem with far point, so he will see far objects will appear blurry to the observer. So he is suffering from myopia or nearsightedness, and the lens we already know it is concave. So this we have already answered. Now for a worst case, we need to consider that the object is placed at infinity. If the object is placed at infinity, then the image must be formed at this far point. Okay, at this far point. So object placed at far point must be formed at the far point of this eye. The far point of this eye is what? Minus 2 meter. So now we calculate 1 by f, which is equal to 1 by v minus 1 by u, which is minus 1 by 2. And this is what? Minus will become plus 1 by infinity, and 1 by infinity, you know, it is 0. So 1 by f is what? Minus 1 by 2, or it is what? Or this is also power of lens also, because we are taking in meters only. 1 by f is power of lens, and this is minus 0.5 diopter. Now negative sign indicates that it is a concave lens, which we know that we need to correct near sight. Okay, this is how you solve these questions. The defect of vision that cannot be corrected by spectacles is, so this answer is cataract. So let me tell you something about cataract. So cataract is what? Over the eye lens, what it becomes? It becomes blurry. It becomes blurry, or you can say it becomes milky like. Okay, milky like it will become. What? Why? Because there develops a membrane over it. The membrane develops over it, and this occurs due to after aging, generally in old age people. Okay, what happened? This membrane develops over it, and it covers the lens, and what happens? This lens becomes nearly opaque. Opaque means what? Light cannot pass through it, and when light cannot pass through it, the vision is very blurred, and this needs a replacement of lens. It needs a replacement of lens, and when it becomes, suppose this milkiness or this blurry, this membrane, sometimes what it happens, there may be total loss of vision of also. Okay, total loss of vision due to this development of membrane and this aging of this lens. It will become blurry. So that is why there may be a total loss of vision. So for correcting this, we make a, or we perform a surgery. Okay, a surgery is the possible treatment to replace this lens only. And this replacement of lens, we replace it with an artificial lens. So we replace it with an artificial lens. And since this involves the surgery and replacement of lens, so it cannot be corrected by spectacles. In spectacles, we are suggesting concave or convex lens, right? So this can be corrected, this can be corrected also. Presbyopia can be corrected, hypermetropia can be corrected, myopia can, but cataract is the one which cannot be corrected by wearing a spectacle. it can be corrected only by performing a surgery and replacing the lens with the artificial lens. So this is all about cataract, and this is all about this chapter. So we have completed this chapter, which is human eye and the colorful world. So thank you.